All right, let's start. Can you hear me well? Okay, so yeah, we are currently studying what is called echelon form. Okay, so the echelon form is the form of the matrix as an output that we obtain through this Gaussian elimination that we studied already, and it has a three requirements or three conditions to satisfy as an echelon form of a matrix. And so we studied the first one, which is any zero rows should be below below the any non-zero rows, right? So that was because we are always choosing some kind of an eraser from the top left, right? So at a certain row, if it is a zero row, and then we will just bring some other row to the top row so that we can have this eraser or non-zero part of of the leftmost variable. And then we will study the second one and the third one. But these are a little bit difficult to understand without the example. So before explaining them in detail, I will just go through a few examples. Okay, so I will also explain it after we look at this example. Okay. So suppose we are given this matrix. Okay. So it can be some augmented matrix of a given linear system. Okay, so let's apply the Gaussian elimination in this matrix. Okay, so we always look at start with the first row, right? And then also the first variable, right? And then we see 0 over here, but in this case we see or we check if any of the lower rows have non-zero values on this first variable, right? So we definitely see three other rows have non-zero coefficient for the first variable, and so we have to switch or interchange any of these non-zero rows to the top row, right? And so in this case, we suppose we chose the last one. Okay, so it's currently an arbitrary choice. Okay, so you can choose any of non-zero values. So if we chose the last one and then we change it or interchange it between the first and the first one, okay, and then we obtain this, right? Okay, and then let's just ignore these pivot and the pivot column because I will explain it after we go through this example. Okay, and then these will be erased by the row replacement, right? And so how? So using this, we just multiply it by 1 and then add it to the second row, right? And then multiply by -2 and then add it to the second row. The third row, right? And then it's already 0, so there's nothing to do for this last row. Okay, so this is the result after we erase this part. Okay. Okay, and then we now move to the smaller linear system, right? And then we do the same thing. Okay, and then using this as an eraser, we erased or made these two elements as 0, right? Okay, and then now we look at this part, but in this intermediate result, we can see all 0 row over here, right? So what should we do? We have to interchange between these two rows, because for the in this case, we see 0 over here, right? But here, let's look at the lower part, and the remaining equation also has 0 values in the corresponding column or corresponding variable, right? So at this moment, there is no eraser, but at the same time, there is nothing to erase, because we have no eraser, but all the lower coefficients are 0, so there's nothing to erase, right? Because if there were any non-zero, and then it will be used as an eraser, and any other non-zeros will be erased by that, right? But in this case, that first column over here, corresponding to this part, will be is completely 0 column, right? So yeah, we don't need to do anything for this column, right? But in this case, from this pattern of like starting from this big linear system, we just kind of reduced the problem size or the size of this linear system by one less equation and one less variable, right? So these parts are gone, and then from this part, we used this guy as an eraser, and then we used this part. We removed this part, and then we came up with a smaller linear system, right? So in this case, the first variable in this smaller subsystem or sublinear system, so the first variable is 0, right? And so we just ignore them, and then we just think of it as the smaller linear system directly by just ignoring the first variable that have completely 0 coefficient, right? So in this case, moving to the smaller linear system of 0, 0 and -5 and 0, and then from there we apply the same algorithm or same process. So in this smaller linear system, we look at the first variable in the first equation, which corresponds to this guy, okay? And then it is 0, but we look at the downward or lower part, and this guy, we can find the non-zero value. So it's time to switch them again, right? Okay, and then we switch them between these two rows. Okay, and then this one will be used as an eraser, but looking at the downward, we see 0, so there's nothing to erase, right? So this is the final result of the first phase of this Gaussian elimination, right? So this example is just a slightly more difficult or more trickier one than the previous one, because we had to do the interchanges, and then in the middle of this process, we found some completely 0 column, and what should we do in this case? We just exclude or ignore that, and then just consider the smaller linear system, and then do the same thing, right? Okay. So this is the result of the first phase of this Gaussian elimination, right? And then, if you remember what I discussed last time, the output of the first phase of Gaussian elimination is called echelon form, right? And then now it's time to study the condition or requirement that this echelon form matrix satisfy, okay? So we only discussed the third condition. Oops. Among these three, right? And then now let's look into the first two, okay? And so, we only looked at the first one, right? First condition, but we now look into the second and the third column, third entries in this three requirements. Okay, and then the second requirement is in this matrix, we now look at the leading entry of each column. Okay, what was the definition of the leading entry? So we are given a particular row, and then we find out the first non-zero element. Okay, so this guy is the leading entry, and what about the second column, second row? This guy is the leading entry, right? And then this guy is a leading entry, right? Okay, and then the first condition of this echelon form matrix or echelon form is we look at this leading entry, and then we choose any of them, and then suppose we chose this leading entry of the third column, third row, okay, and then which row is it? It's the third row, right? And then from this leading entry, we now look at the upper rows, which are the first two rows, okay? And then each of these first two rows also has their own leading entry, which is, which are located over here, right? And then we look at their column position, okay, column position. So again, the process is, you can choose any of them, and then now suppose we chose the last one or the third one, okay? And then starting from there, we now we look at the upper rows from that entry, and then among these upper rows, we find out the leading entry of each of these upper rows, which are these two, okay? And then now look at their column position, and then the column position is the first one, the first column. And then what about this? So this is the second column, right? And then, so this was the starting point. And then what was the column position of that leading entry? So it is 1, 2, 3, 4. 4, it's placed in the fourth column, right? Okay, so from this pattern, we can see that looking at the upper rows, and then the leading entries of these upper rows are placed on the left columns or left part, which means if it was placed on the fourth column, right, and then looking at the upward, and then upper rows leading entries should be placed on the left of this leading entry, okay? So this is the first condition, and then this condition should be satisfied for any of leading entries that we have in our matrix. Okay, so in this case, let's now choose this guy as our leading entry. Okay, for that one, we need to satisfy the exact same condition. But in this case, we now look at the upward, and so this, this row is the only upper row, right? And then what is the leading entry? Leading entry is on the first column, and then it's still on the left side of this leading entry that we start with, right? Okay, so intuitively, this second condition, is telling us the matrix structure in terms of their leading entry in this form. So suppose we have maybe 4 rows in our matrix, okay? And then now, you know the definition of the leading entry, the first non-zero entry for each column, right? And then suppose the leading entry is found like in this, okay? So does it satisfy this condition that we discussed? It's not, right? Which one doesn't satisfy? Okay, for this guy, does it satisfy this condition? Yes, right? Because we look at the upper rows, and then for the leading entry, and they are all on the left side of it. But if we choose, what if we choose this guy? Okay, we look at the upper row, this guy, and the leading entry is found actually on the right hand side, the right part, right? And for this guy, yeah, this guy is the wrong one as well, right? So this is the first placed on the first row, and then the upper part of the leading entries are found on the right, right? So this one is clearly not a echelon form. Okay, so from this pattern, yeah, we can have some kind of intuitive ideas or understanding about the pattern of the leading entry positions of our matrix in this form. Okay, so if we had this 4 entries, 4 rows, suppose we found the leading entry over here in the first row, and then for the remaining rows, their leading entry should be always placed on the right part, right? So something like this. And if we found the leading entry is over here, and then for the lower rows, and then their leading entry should be placed over here. Okay, so intuitively, this echelon form, you can think of it as a kind of a staircase shape. What it means is, so if this guy was a leading entry, and then all the left entries of this leading entry should be 0, because that's the definition of the leading entry, right? So it should be all 0, right? Because that is the definition of the leading entry. And then we can draw this kind of pattern. Okay. So what about this part? Okay. So we don't care about this part because they can be either like 0 or non-zero, right? We only care about the leading entry, or the first or leftmost non-zero entry of each row. Okay, and then yeah, we can see this kind of pattern, right? Okay, and then now we have one last requirement of the echelon form. The last one is relatively easier than this condition. So that condition is as follows. So in this matrix, yeah, we also think of this non-zero element in our leading entry of our matrix, and then for each leading entry, we now look at the lower part. Okay, lower part. So the lower part should all be 0. Okay, so if we found any leading entry in every row, okay, and then we just look at the downward part, and then in the corresponding column, the lower entries should all be 0. And that is a kind of natural pattern that we just easily obtain because through this Gaussian elimination process. Because yeah, what is the Gaussian elimination process? We pick up some non-zero element, and then we remove all the coefficient in the lower equations by using the first equation as an eraser, right? Because we erased all the non-zero parts in the lower equations. So this condition is naturally satisfied through this Gaussian elimination process. Okay, so in this case, can we think of some special case or some cases where the second condition is satisfied but not the third condition? I mean that, yeah. In other words, yeah, some matrix is satisfied with this kind of a staircase shape, okay, but for this matrix, it doesn't satisfy the last condition, that for each leading entry, all of them should be 0. So this one is not satisfied. Is there any cases? Yeah. Is there any such cases? Yeah, actually, I haven't thought about this case, so can anyone give an example of that pattern? So the second condition is satisfied, but the third one is not satisfied. 불가능해요?
앞에 무조건 0이 있어요. 여기가 리딩인데 리딩 0이 있어요. 여기 무조건 밑에
그러네요. 그럼 저기 왜 다른?
이거는 말이 안 되는. 이걸 하면서 만족을 안 하시는 직관적으로
그죠? 나도 그렇게 생각했는데 왜 저게 두 개 컨디션이 따로 있을까요, 그러면? 네? 클래리피케이션? 네. 아, 네. 이거 네. 그래요. 이걸 내가 이 과목을 가르치는 게 이제 5년째인데 이걸 한 번도 생각을 안 해봤더니. Yeah. 네, 한번 뭐 나도 조금 더 생각을 해볼게요. So, yeah, I guess these two, yeah, the second condition is satisfied, and then it naturally leads to the satisfaction of the third condition. Yeah. But yeah, I'll see if I can find some other counter example. But at least you guys understand those two conditions, right? So altogether, if these three conditions are satisfied, including the first one that we discussed last time, and then this matrix is called echelon form. Okay. So now we understood the output of the first phase of this Gaussian elimination will just naturally satisfy all the conditions of this echelon form, and so okay, and then now let's think of the second phase of this Gaussian elimination. The second phase is going upwards, right? And so see. Okay, then in order to see this second phase of this example, and we'll let's use another example of this matrix. Okay. Okay, and then we start with this guy, and then it's time to interchange between these two rows. So we change it, the first and the third row in this case, and then using this we erase this guy, right? And so we make it a 0, and then the remaining process is the same. So this guy will be our eraser, and then we erase this part. Okay, and then now, yeah, we have this linear, yeah, this smaller linear system, and we only have one equation. And then now we look at the leading entry, but there is no other, yeah, no other lower rows, so there is nothing to erase. So that's when to stop. Okay, so this is the first phase output. Okay, and then now let's apply the second phase, going to the upward. Okay, so from here, by using this, okay, so using this leading entry, we now remove these two, right? How do we remove them? We just multiply from here, multiply negative with the -2, and then add it to the second row, and then multiplying it with the -6, and then add it to the first row, right? And so that's how we make those two elements as 0, right? Okay, and then now we look at this upper part, and since this variable was eliminated, this part is the the smaller linear system that we consider during this second phase of Gaussian elimination. Okay, so in this case, which variable should we use as our eraser, and also those variables to be erased. So in this case, in the previous example that we saw last class, it will be this variable, right? Because we always look at the rightmost variable or column, right? And so we can erase it by using this guy, yeah, for this entry, right? But here, this second phase is not, yeah, is not working in this manner. Okay, so we always use this leading entry of this smaller linear system. Okay, so in the upper phase, yeah, we look at this part, but which one or which variable is used as our eraser, it is always used as a leading entry in that column. Okay, so using this, we erase this value. Okay, but before doing so, during this second phase, we always scale our eraser as having the coefficient of 1. Okay, so in this case, so this was already 1, but this one is 2, and so we scale it by 1/2. And so we first, yeah, we first scale this row by half. Okay, and then using this, we just multiply this by 9 and then add it to the first row. Okay. Okay, and then this is the result of this second phase. But here we erase this part, and then now we move to the top part. Yeah, further in this case, and so we consider this part, which is a smaller linear system. And then here, even though we don't have any other upper rows than this guy to be erased, but in this case we can use, or we can apply the scaling of the first row. Okay, so this guy is scaled by 1/3, so that this value is 1. Okay, so the second phase, yeah, seems a little bit arbitrary in terms of, like in this part of this smaller linear system where we erased this part. So we consider those variables on the left, but which variable to erase? So using this, do we erase this guy, or using this, do we erase this guy or this guy? So we have different choices, right? But yeah, it's not a right or wrong kind of sense of our strategy, but we just apply this specific rule to make this algorithm consistent. We always stick to the leading entry, and we always use that as our eraser. Okay, to erase the corresponding variables in the upper rows. Okay, so in that case, if we follow this particular rule, and then this guy will be used as our eraser, and then this part will be erased. Okay, so this is the second phase of Gaussian elimination, which results in this final result. Okay. Okay, and then after doing this second phase and completing this second phase, the resulting matrix is called reduced echelon form instead of echelon form. Okay, so reduced echelon form is more strict version of the echelon form that satisfies the two additional requirements or conditions. Okay, so reduced echelon form, which corresponds to the output of the both phases of Gaussian elimination, which is the last or final result. Okay, So in this case, the resulting matrix is called the reduced echelon form, which additionally satisfies these two conditions, yeah, on top of these three conditions. Okay, so let's look at these two additional conditions for our reduced echelon form. Okay. Okay, so in this case, the leading entry should be always 1. Okay, so that is quite simple condition. So in this final output, yeah, we look at the every leading entry in every row. So this guy and this guy and this guy. Okay, so all these leading entries should be 1. Okay, and this was simply satisfied or achieved because during the second phase we always scaled it so that the leading entry is 1, right? And the reason is because we wanted to use it as a kind of easy eraser, right? Because if it is 1, and then we can simply multiply, like, yeah, so in this case, if we want to erase this guy by using this, and then we had to multiply like 9 over 2, right? So we don't want this kind of denominator, right? And so to make this simple, we always make this guy or our eraser as having the coefficient as 1, right? So that simple scaling of a particular row or single row, will make the resulting matrix satisfy the fourth condition of, or the first additional condition of reduced echelon form. Okay, and then the fifth condition, or the second additional condition, is as follows. So in the echelon form, one of the three conditions was telling us that for each leading entry in every row, and then we look at the downward part. Okay, so these parts should all be 0, right? But at the same time, once we do the second phase of our Gaussian elimination, not just the bottom part, but the upper part of that leading entry, I mean along the vertical line, should all be 0, right? So in this case, let's further apply the second phase of this matrix on the by using the Gaussian elimination. Okay, and then we always look at start with the last column, or last row, and then we just simply scale it by 1, right? And then the scaling should be done on the entire row, but they all have zeros, right? So yeah, by just multiplying -1/5, and then this one will change it to be 1, then all the other values will remain as 0, right? And so this guy became 1. Okay, and then now by using this, we have to erase these two, right? And then how do we erase it? Yeah, so if it is 1, then we just multiply it by 6, and then add it to the second row. Okay, and then it will be 0, right? And then what about this value? This value will remain the same, because this times 6 will also be 0, right? Okay, and then what about this guy? So it will be also 0, right? Okay, and then now we move to the one row, one upper row, right? And so in this case, so we look at the leading entry as well, and then the first thing to do is to scale it so that this leading entry will be 1, right? Which can be working as a easy eraser. And so let's scale it in this case, and then this value should be 1, right? And then this should be 2, right? And then this became 0 in the previous step, and then this becomes -6, -3, right? through this row scaling, right? And then what's the next step? We erase this value, right? Yeah, it's getting a little bit messy, so let me just rewrite the intermediate result so far. It's 1, 2, and 0, and -3, and 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. Okay. Okay, and then we have to erase this guy, right? And so we multiply this equation by -4, and then we make this value as 0, and this value will be -3, right? And then 12, this guy will be 5. Okay. Okay, so now this is the final output of this Gaussian elimination, and let's look at each row and then find out the leading entry. So these are the leading entries. So those are all ones, right? That satisfies the first additional condition. And then now, what is the second additional condition? For each leading entry, not just the lower part, but also, it should have been 0 over here while using this guy as an eraser, right? Right? Okay, so this upper part is also all 0, right? So what about this guy? So for this leading entry, the lower part is 0 through the due to the first phase of Gaussian elimination, but during the second phase, that erases the corresponding variable in the upper equations. These are also be 0, and for this guy, they are 0, but there is no other upper part, so it also satisfies this condition of like the upper entry of any leading entry should all be 0, right? So in this case, I mean, these two are the additional constraint of reduced echelon form. Okay. So in the case of a reduced echelon form, it is already a echelon form that maintains this staircase shape in terms of the first non-zero entries or leading entry of each row, and then once we picked up or once we collected all these leading entries, and then we look at the downward part or the upward direction or downward direction, all the elements should be 0, which means if a particular entry was a leading entry in any of our columns, in any of our rows, okay, and then vertically that entry should be the only or the unique non-zero element in that corresponding column. Okay. Okay, so although it's a little bit messy, but if we found this echelon form, and then this lower part of each leading entry should be 0, but we now look at the upper part. Okay, upper part should all be 0 as well, in order to be a reduced echelon form. Okay, so that is described as the fifth sentence. So each leading entry is 1, as described in the first item, and then this is the only non-zero entry in its column, or vertically, that should be the only non-zero one. Any questions so far? So it's a little bit tricky, or it might have been a little bit verbose to explain all these properties, but the homework will be posted soon. I mean, the first homework, so that you can do your own exercise to make this matrix into echelon form, or reduced echelon form, and then you will see, you will easily understand this kind of patterns or requirements for echelon or reduced echelon form. Okay. And then now let's study a little bit new terms related to this echelon or reduced echelon form. So we understand the leading entry, which is the first non-zero entry in a particular row, right? And suppose our matrix is echelon matrix or echelon form of a matrix. Okay. In this case, the leading entry has a special name. I mean, another special name, which is a pivot. Okay. Again, your matrix is satisfying the echelon form or the requirement of the echelon form. And in that case, those leading entry in that matrix is not just a leading entry, but they are especially called a pivot. Okay. So, for example, let's see. This matrix, as it is, or initially, it is not satisfying the echelon form, right? But still, we can call the leading entry, or we can find the leading entry, which are this guy is the leading entry simply because it is the first non-zero entry in the first row, and this guy is the leading entry, right? And these are also the leading entry, right? But they are not called a pivot because this form is not an echelon form. Okay. But once we obtained the echelon form matrix and then the corresponding leading entry, let's see, of this guy or this guy or this guy. Okay. So these are not just a leading entry, but they are called a pivot. Okay. Okay. And then now we can think of the pivot position, okay, where you can find those pivot entries or non-zero entries in the case of echelon matrix or echelon form of a matrix. Okay, so the position contains the information of like the row index and the column index. So in this case, the row index is 1 and the column index is 1. Okay, in this case, it's a 2 by 2. So it is like the first, second, and the third, and the fourth row, and the first and second, and the third columns, and so on. Okay, and what about this guy? This guy is the leading. This pivot has the position of 3, 4. Right. So. So these are these are the pivot position, and in terms of this pivot position, some important meaning is conveyed in especially in the pivot column position. So we care much about this column position of our pivot. So in this case, among these 3 pivots that has these position indices, and then what is the column position of all of our pivots? The first column, and second, and fourth column, but not the third column or fifth column, right? So in general, in this matrix, purely looking at this matrix as it is, we have 5 different columns, right? But only the first, second, and fourth one contains the pivot, but not the second and the fourth, not the third and the fifth. Okay, so you will see that's kind of a whether a particular column contains a pivot or not. I mean, this information will work as an important information to determine whether our linear system has a solution or not, or if it has a solution, and then whether this linear system has a unique only one unique solution or infinitely many solutions. We will study this this kind of relationship between the the pivot positions in terms of their column indices, and also the number of solutions or the existence of our solution. Okay, so in this case, Yeah, let me ask one kind of related but simple question. Is it possible that a particular column has multiple pivots? So again, the question is, for any given column, is it possible that this column has multiple pivots? Yes, it is possible, or no? Okay. Okay. So I think, most of the students are right. So in this case, this is the example. So here, let's look at the leading entry over here. So those 4 leading entries, and their leading entry positions are like is 1, 2, and 2, 1, and 2, 1, 3, 1, and 4, 1, right? And then the first column has multiple leading entry in the second, third, and fourth, right? Okay, so in this case, in a particular column, there exist multiple leading entries, right? But we do not call them a pivot because we should satisfy, or we only consider echelon matrix or echelon form of a matrix. Okay, so if we consider this echelon form of a matrix, okay, so in this case, we have these 3 columns, right? And then each column, is it possible to have a multiple pivots? Suppose, let's consider the second column in this case. So this one is currently our pivot, right? And then suppose this guy is also our pivot, okay? And then would it be possible? If it will not be possible, because if this guy was our pivot or the leading entry of some upper row, okay, and then this guy, would not be able to be survive, because this one will have been already erased by using this as our eraser, and then all the lower entries should have been erased already, right? Okay, so there is no way for this guy to survive as non-zero entry once this guy was our pivot in the previous step or in the lower row, the upper rows. Okay. So in general, once you obtain the echelon form, and then any column or particular column will have only one pivot at most, or it may not have any pivot at all. Any questions so far? Okay, so let me add one additional clarification. So this guy is pivot, right? And then those are not called a pivot, right? Because they are not. They are non-zero entries, but they are not called a pivot because they are not the first leading entry, or they are not the leading entry in the corresponding row, right? So even though they are non-zero, they are not called a pivot, because pivot in the corresponding rows will be somewhere on the left-hand side, left part. Okay. Any questions so far? So you guys prefer to have a break in the middle of our lecture Monday, right? Right? Okay, so let's have a break until 1 p.m. and then we will resume after it. After then.
이제 그냥 정의상 궁금한 게
네.
이제 교재상으로는 이제 reduced echelon form일 때 pivot position이 된다고 돼 있는데 이게 뭐 정의는 reduced가 아니더라도 그냥 echelon form만 취해도 pivot이라고 하는데 reduced는 이거 좀 잘못된 정의 아닐까요?
그러니까 에슐론 폼에서의 리딩 엔트리가 피벗이라고 불리고요.
네.
그 다음에 이제 리듀스드 에슐론 폼도 에슐론 폼의 일종이잖아요.
네네.
그래서 이제 리듀스드 에슐론 폼의 리딩 엔트리도 역시 피벗이라고 불려요, 당연히.
네네.
근데 이제 여기서 이제 마치 이제 정의처럼 이제 피벗은 이제 리듀스드 에슐론 폼에서의 뭔가 그거다라고 이야기를 했는데, 네, 이거는 뭐 잘못된 거라고 보면 돼요. 그러니까 정확한 정의나 어떤 피벗의 정확한 정의는 리듀스드 에슐론 폼까지 안 가고 에슐론까지만 네, 가서 거기서의 난지로 엔트리를 리딩 엔트리를 피벗이라고 불러요.
네, 뭐 피벗 포지션은 reduced에서만 사용하는 그런 용어는 또 아니에요.
네, 맞아요.
잘못된 거.
네,
네, 알겠습니다.
맞아요.
피벗이
네.
그 얼규먼트 매트릭스에서 여기일 수도 있어요?
네.
00003이면?
그렇죠. 그럴 수 있죠.
그러면 그러니까 상수가
네.
피벗이 될 수도 있는 거예요?
그렇죠. 네.
아,
그러니까 그게 되게 중요한 요소인데 뭐 그거를 아마 이제 설명할 텐데 그렇게 될 수 있어요. 예를 들면 뭐 그냥 우리가 심플하게 이런 매트릭스 예를 들면 뭐 2, 2, 3, 4, 4, 7 이러면 이제 얘를 가지고 얘를 지우잖아요. 0, 0이 되고 여기 1이 되잖아요.
네.
그러면 뭐 지금 이렇게 됐잖아요.
네.
그러면 얘가 피벗, 얘가 피벗이에요.
아,
그렇죠? 그러니까 여기 이제 1이 될 수 있어요. 근데 이게 last column은 그러니까 last column 빼고 그 왼쪽 것들은 다 베리어블에 해당이 돼요.
네.
그죠? 근데 last column은 이게 이제 우항에 있는 게 상수들을 의미하잖아요. 그래서 이제 어떤 로우가 피벗이 가장 오른쪽에서 발견이 됐으면 이거는 이제 뭘 얘기하냐면 이 이퀘이션 그렇죠. 해가 없는 경우에 해당이 돼요.
근데 그러면은 이런 경우가 있으면요.
네.
그 돌릴 그 뭐냐 그 위로 올라갈 때 나머지는 다 0이 되는 거예요?
네. 이 경우에도 이제 예를 들면 여기가 2, 2, 3이었고 여기가 0, 0, 1, 1이 됐으면 이거는 에슐론 폼은 맞아요. 근데 이제 이거를 이제 리듀스드 에슐론 폼으로 만들고자 하면 만들 수 있죠. 0, 0, 1을 이거를 가지고 얘를 지우면 0이 되고 0이 되고 이렇게. 그러면 이제 2가 되는데 여기서 이제 얘를 또 스케일링을 해주니까 1, 1이 되는 게 맞아요. 네. 그래서 지금 보면 이렇게 돼 있고 얘랑 얘가 피벗이고 얘 위아래로 다 0이고요. 그렇죠? 그리고 얘네들은 1이고 또 이 계단을 만족하고 그러니까 이거는 이제 그 리듀스 에슐론 폼 맞아요. 네. 그래서 이제 그 해가 있든 없든 우리가 가우시안 엘리미네이션을 포워드 및 백워드로 이제 끝까지 다 해서 우리는 언제나 리듀스 에슐론 폼을 얻을 수가 있어요. 네. 그렇지만 이제 해가 있냐 없냐는 벌써 에슐론 폼 그러니까 포워드 페이지에서 판정이 나요. 그냥 피벗이 라스트 컬럼에 있으면 그러면 해가 없는 거예요.
지금 하고 있는 거를 한국말로 하면 지금 행사다리코 그걸 만들어.
네 맞아요.
그걸 만들어가지고 그 다 일로 만드는 게 지금 그거를 뭐라고 하나? 한국말로?
그 형태 매트릭스
네.
형태를요. 에슐론 폼. 네, 에슐론 폼. 그게 아마 무슨 사다리 꼴 뭔가 할 텐데.
근데 그 만약에 밑에 아까 전에 0000000이 있던데
네.
이런 건 왜 있는 거지?
그런 거요. 그러니까 이제 지난번에 이제 그 이야기를 했던 그러니까 여기서 우리가 봤던 요 이제 첫 번째 컨디션 요거 있잖아요. 이제 요거가 이제 그거에 해당이 되는데 보면 일단 처음에 뭔가 0인 컬럼이 발견이 됐다. 가장 위에서부터 볼 때 0인 컬럼이 발견이 됐으면 걔를 일단 우리는 밑으로 내려갔고 뭔가 그 어떤 베리어블 첫 번째 베리어블의 난제로 값이 있는 애를 이쪽 올리잖아요.
네.
그러면 또 밑에서도 또 얘는 또 완전히 0이니까 얘는 0으로밖에 남아있을 수가 없고 또 밑에 거랑 또 대결을 하다 보면 또 얘는 밀릴 수밖에 없어요.
네.
그래서 결론 아니면은 이제 중간에 이제 어쩌다 보니까 0이라는 완전히 0인 로우가 튀어나올 수는 있어요.
네.
네. 근데 중요한 건 그렇게 됐을 때는 걔가 또 그 다음 번째에선 또 이제 밑으로 내려가게 되죠.
근데 만약에 그러면 0000 만약 예를 들어서 지금 4 곱하기 5가 있는데 맨 밑이 0000이면 근이 뭐 예를 들어서 x1이랑 x2랑 x3랑 x4가 있으면
네.
다 하나로 왜 문자로 정리를 해야 되는 건가요?
해를
근이
구할
안
때
나오니까.
네. 맞아요.
아 그렇게 안
맞아요. 그걸 우리가 지금 또 배울 거예요. 네. 네.
아까 그 컨디션 애슐리 컨디션에서
네.
2, 3번이
네.
2번이 될 때 3번이 안 되고 그런 게 없다는 거 쓸 수 없다는 거.
그러니까 가우시안 엘리미네이션의 첫 번째 스텝을 하면 이거 두 개는 다 만족을 하는 거는 맞아요. 근데 그냥 에슐론 폼의 그냥 순수한 요 세 가지 조건에서 볼 때 두 번째 거는 만족하고 이제 세 번째 거는 만족하지 않거나 혹은 이제 하여튼 둘 중에 하나만 만족하는 케이스가
있어요. 있을 수가 있어요.
그걸 나도 모르겠어요. 생각을 해본 적이 없었어요 지금까지 나도. 그래서 있나? 네, 한번 그거를 네.
세컨드 페이지에서
네.
그 올라갈 때
네.
여기서 그러니까 리딩 엔트리가
네.
이레이저가 되는 거고
네네네.
근데 만약에
네.
그 올라가야 할 때 만약에 여기 그 윗줄에 만약 마이너스 9가 아니라 0이
마이너스 6가 아니라 애초에 0이었다.
애초에
0이었으면은 우리가 아래 거를 지울 때, 그러니까 포워드 페이지 첫 번째 페이지에서 아래 거를 지울 때도 0인 애는 아무것도 안 해도 되잖아요. 그러니까 얘도 마찬가지로 위에가 원래 0이었다 그러면 걔는 안 지워도 되는 거죠.
그냥 그대로
두면 되죠.
두는 상태가 그리고 그냥 리딩 엔트리 1로 맞춰놓기만 하면 그게 최종 상태가
맞아요. Alright, let's continue. Okay, so we now fully understand the meaning of this echelon or reduced echelon form, which are just an output of the forward phase and the backward phase of our Gaussian elimination, respectively. Okay, and then we now understand each of our requirements or condition to satisfy as a echelon and reduced echelon form. Okay, and then now it's time to relate or utilize resulting reduced echelon form to obtain the solution of our linear system. Okay. Okay, so let's look at this example. Let's first check if this matrix is either echelon or reduced echelon form, or neither of them. So let's look at the leading entry of each row, okay, and then they have this staircase shape, right? So staircase means like, it's like a gravity is not coming from the top to bottom, but from bottom to top, okay? And then, you can think of some person is standing in the reversed direction, okay? So that's why, that's what I mean by a staircase shape, okay? Okay, and then yeah, related to this staircase shape, let me also ask one related question. So, is it possible that this staircase shape so what I mean is something like this. Okay, so is this echelon form or not? It's not. Why? Yeah. Okay. So yeah, let's look at the leading entry at each row, right? Okay, and then for this leading entry, this guy should have been erased, right? Which makes it impossible to have another leading entry or pivot in this lower rows, right? Okay, so in this case, yeah, you can think of like this guy, yeah, can move to the lower part of this staircase shape, okay, but if the staircase is too deep, okay, with the two level differences, okay, it is not possible that this guy comes down properly without injury, okay. Okay, so the level difference or height difference at each staircase shape should be always 1, okay. But what about this case? Okay. Yeah, something like this. So is this a echelon form? It is, right? And in this case, yeah, following this staircase shape, yeah, it's yeah, one level down, right? And then even if it's a little bit flat, so we have no problem of moving horizontally with our legs, okay? In this case, it is okay. Okay, so back to this example. So this is the echelon form. Is this reduced echelon form? Is it not? Why? It is a reduced echelon form. It is just an echelon form, but not reduced echelon. Why? Why do you think it is not a reduced echelon form? 이야기해 줄 수 있어요? 왜 그런지? 이거요. 네. 좋은 지적. 그러니까 이게 okay, so there is a really pitfall that that is easy to fall in. So in this case, if we think of this non-zero entry, and then yeah, we feel like, or we kind of get some urge that this guy should also be 0, but yeah, it doesn't need to be that way because we only consider the leading entry, right? Okay, so these two are only the leading entries that we have. So about this case, this one is not our leading entry, so that will not be used as our eraser to erase the lower part or upper part. Okay, so we only use those pivots or leading entry in our echelon form as our eraser to remove the lower and the upper part of the entry. Okay, so this is echelon reduced echelon form because they are all ones and they're looking at the downward on upward, and they are all 0, right? So we do not care about these rows because they don't contain the pivot or leading entry. Okay. Okay. And then let's just reconstruct or consider this corresponding linear system after we obtained this leading reduced echelon form. Okay, so in this case, the first equation is corresponding to x1, yeah, 1 times x1 and 0 times x2 and negative 5 times x3 is equal to 1, right? And then 0 times x1 plus 1 times x2 plus 1 times x3 is equal to 4, right? And then, yeah, even though we had the third equation, this third equation became like nothing after we convert our matrix into reduced echelon form. Okay, so in this case, I mean, what would be the corresponding case of having initially some equation, but they are gone after after computing this Gaussian elimination. So in this case, the simple case is like this guy, x1 in this case, let's imagine it's augmented matrix, and then it's a 1 2 3 2 4 6, and then by using this we erase this guy, but while erasing this value as 0, and then the other values become also 0, right? And there is this simple case, but also there could be some other a little bit non-trivial cases. So in that case, I mean, 1 2 3. Okay, so let's look at this example. So we initially have 3 equations and maybe two variables in this particular case. So in this case, if you do the Gaussian elimination, and then this the third row will be completely gone. Okay, I mean, I will skip the actual computation. Okay, but I'm gonna give you some intuition about why this guy should be gone after doing this Gaussian elimination process. And so how I constructed this example is this guy and this guy. So suppose using this, suppose we erase this guy, 0, and -1, -2, and so on. So the second equation will not be completely 0, right? Because the ratio between 1 2 3 and 2 3 4 are different, right? But we remove this, we also erase this guy, and also once we use this guy as an eraser to erase the last equation, and then it should be gone, because in this case, the summation, or if we add the first and the second equation, and then we automatically obtain the last equation or the third equation, right? If we just add x1 and those two, and then we obtain 3 and 5 and 7, right? So the third equation doesn't give us any additional information or constraint to satisfy. Okay, so once we obtain, suppose we obtain the solution that satisfies the first 2 equations, and then that solution will just automatically or always satisfy the third equation, right? Because the solution that already satisfies the first 2 will be just automatically, will automatically make the third equation true. Okay, but you will see those examples, and also we will see these relationships in more detail in the later slides or later chapters. But I'm gonna give you this kind of simple intuition by using this example. Okay, so yes, now we understood we cannot. It is possible to obtain completely 0 equation out of initially non-zero equation, right? Okay, so in this case, the third equation is completely 0. So this equation is no longer be used. Then these 2 equations are will give us the final solution. But in this case, is this the final solution that we can obtain? I mean, if we rewrite it, then these 2 equations are the final result after this Gaussian elimination. So typically in this case, 1 2 3 and 3 1 4, for example. And then in this simple example, we will make 0 by multiplying it by -3 and then add it. -5, -5, right? And then using this, we make it as 1, right? By just using the row scaling, and 1 and 1. And then we using this, we now use the second phase, and so it will be just 0 and 1, right? So altogether 1 0 1 0 1 1. Okay, so in this case, the corresponding linear system, if we consider the corresponding linear system, and then let's look at the last equation first, and then in this case it will give us x2 as 1, which gives a specific or the particular value as our solution for the second variable, or x2, right? And then the first equation is x1 is equal to 1, right? So in this case, the unique solution will be obtained if our reduced echelon form is shown in this manner. Okay, but in this case of our reduced echelon form, this last equation, x2 and x3 is equal to 4, x1 plus or negative 5x2 is equal to 1. So it doesn't give us the specific value of any of our single variable, right? So this is the best that we can obtain as our solution instead of having a specific solution. So in this case, it means that our solution is infinitely many. Okay, the number of solutions are infinitely many. Okay, and in order to represent our solution as this infinitely many solutions, we now consider those columns that contains the pivot and those other columns that doesn't contain the pivots. Okay, so in this case, so pivot is found over here, and the first column is the pivot column, and the second column is also the pivot column, which contains the pivots, but not the third column, right, which doesn't contain any pivots. So in this case, so this column is corresponding to x1 and x2 and x3, right? So in this case, the variable corresponding to the pivot column is called the basic variable, and the variable corresponding to the non-pivot column is called free variable. Okay, so here x3 is free variable, but x1 and x2 is basic variable. Okay, and what about this case? So suppose this guy is also 0. So in this case, maybe 2, and this should be 0, for example. In this case, I wanted to make another similar staircase or reduced echelon form, where we find the pivots over here, and then all 0 and all 0, right? So let me rewrite it. 1 2 0 1 0 0 1 4 and 0 0 0 0. Okay, so we consider slightly different reduced echelon form matrix. Okay, so we have a pivot over here, right? Okay, so in this case, let's consider the pivot columns, which are these two, right? And so here the basic variable is x1 and x3, and x2 is now a free variable, right? Okay, then given this reduced echelon form, we just convert it into this equation form, okay, back to this equation form, and then our final solution is represented by just changing this equation to have all the basic variables to be placed in the right and left hand side, but all the free variables are moved to the right hand side. Okay, so in this case, again, back to this original example, we know that the first and the second variables are basic ones, but not the third one, which is the free variable. And so, given this, we just move those free variable part, which corresponds to x3. Okay, so we move them to the right hand side. Okay, and then now our solution is represented in this form. Okay, and then why do we call this x3 as free variable? What's their intuitive role in this final solution? The role of these free variable is, we can freely assign any values to these free variables. Okay, so in that case, those resulting solution will always satisfy the given linear system. Okay, so here, for example, suppose we plug in maybe 0 for this x3, and then what will be our solution? x1 will be 1, x2 will be 4, right? And then using this set of solution, or this particular solution, will just satisfy our linear system. And we can also use another value for x1, x3 as 1 or -1, basically any real value. Okay, so in all these cases, those solutions will always satisfy this given linear system. Okay, and then now, this kind of a representation. Okay, this kind of representation, which is like, let me remove this part, and x3 is free. So this one will be like parametric kind of solution of our linear system. Okay, so for example, this one will be the final answer if you are given this linear system, and then have to solve solve this equation. Okay, so in this case, clearly the solution is not unique, or the solution is infinitely many, right? And its intuitive meaning is as follows. So in this case, we have 3 equations and 3 variables, right? And in general, you have some ideas that if we have the exact same number of variables and equations, and then generally the solution will be determined as a unique one. But if we have like smaller number of equations than the number of variables, and then we know that the solution is infinitely many, right? So for example, in this case, we have 3 equations and 3 variables, but it turns out that the third equation is no longer exists, right? So in this case, we have 2 equations and 3 variables, right? So that's why we have infinitely many solutions. Okay, and some systematic or consistent way of representing our infinitely many solutions is by using this free variable. Okay, so this is the free variable that we can literally freely set as an any value. Okay, and depending on them, the other variables will have the representation in terms of these free variables that will be determined based on a particular assignment of our free variable value. Any questions so far? Okay, and then let's point out. Let me point out one more thing over here. So in this example, so this is the corresponding linear system once we obtain the reduced echelon form. Okay, but we can just So here, even though this one is not a standard or typical kind of a steps that we have to do in the during the Gaussian elimination, but somehow, suppose we just remove this guy using this as an eraser, and then remove this guy. Okay, and then what is the resulting equation in the first row? And then we have to multiply it by 5 and then add it to the first row, and then it should be 5 and 0 and then 21. Okay. Okay, so in this case we made it as 0, and so the first equation is x1 plus 5x2 is equal to 21, and then x2 and x3 is equal to 4, right? So in this case, because this value became non-zero, right? So it's no longer be a reduced echelon form, because this one is still a pivot, but this guy is no longer be a 0, so it's a non-zero, so it's no longer satisfying the reduced echelon form, right? But still, that is a consistent with the, or that is equivalent to the previous one, because they maintain, or they still maintain the same solution set, right? Because the row replacement is the valid operation that doesn't change the solution, right? So in this case, we can represent the solution as this form. x1 is 21 minus 5x2, and x3 is equal to 4 minus x2, and here x2 is our free variable, right? So x2 is just freely set as in any value, and then x1 and x3 are correspondingly determined. Okay, so that is also valid solution, right? So there is no unique way, because the solution is infinitely many. So which one is the starting point or the starting variable that we can freely choose, and then the other variables are correspondingly determined. Okay, so there are many choices, right? But we always find the specific or predefined rule, just like what we did in during the forward and the backward phase of our Gaussian elimination. So if you remember, in the case of backward elimination, let's see. Okay, so so this is the intermediate step of our backward elimination. So in this case, we removed all these, right? And so, as I mentioned, we look at this part, right? And so it's we can use this guy as our eraser to erase this guy, or alternatively, we can use this guy as our eraser and erase this value, right? So this is also another valid row replacement, but that doesn't follow our predefined or our cleanly developed Gaussian elimination process, because it will no longer give us the reduced echelon form or kind of echelon form. Okay, so that will break out this echelon form or reduced echelon form, right? So we always stick to the leading entry and in the both of the forward and the backward phase. We use them as our eraser only for the pivots or non-zero entries. Okay, so like this case where we follow this specific rule, although there could be many different ways of introducing the zeros in our augmented matrix. In this case of representing the general solution, okay, of a given linear system, and then even though we have a multiple different ways of specifying a particular variable as a free variable and and so on, but we always stick to this specific way of, like as I mentioned, once we obtained reduced echelon form, and then we follow the specific rule that the free variables are moved to the right, which work as a kind of starting point of an arbitrary value that we set initially. Okay. So in this case, if even though this one, so in this case, this one is also another valid solution for the same linear system, but we don't represent our solution in this manner. Okay, because in that case, the solution could be it will not be consistent in term so the two of the students solve the same linear system, but their solution may be different, although their solution might be actually indicating the same set, but their representations as to which one is set as a free variable or which one is not. I mean, the solution representation of our solution could be different depending on these different way of solving this linear system. So in order to have always the same solution set, okay, we follow this specific rule of Gaussian elimination to obtain the reduced echelon form, and then move all the free variable to the right, okay, which will be our free variable. Any questions so far? 다 이해 가요? 뭐 질문 있으면 한글로 해도 돼요. Okay. So this is the final form of our solution, which moved the free variable to the right, and then that is called a parametric description of our solution. And what is our parameter? Parameter is our free variable. Okay, so we can freely choose those free variable, and then all the other variables are determined correspondingly, right? So in that case, we can view it as a kind of parameter. So I'm not sure if you guys I mean back in my middle school kind of studying in this case, we can represent the solution of this in this form. 5t plus 1 and x2 is negative t plus 4, right? So t is any value. Okay. So in this case, t is really our parameter that we can freely choose, right? And depending on them, x1 and x2 is determined, right? So in this case, t can be viewed as our parameter to control our solution, right? But still, in this case, those parameters are our free variables. Okay. And then now it's time to answer or consider how to utilize these free variables to determine whether our solution is unique or not. So as we can see, if we have a free variable, at least one free variable or more, okay, in that case, our solution will not be uniquely determined, and so that's the case where we have infinitely many solutions, right? So free variable will give us infinitely many solutions, okay? And I mean, you guys are writing this kind of sentence, but this one is not perfectly true, because we have to consider some other kind of patterns or other cases. So that other case that we have to consider is described in this theorem. So one kind of student asked the exact same question about this issue during the break. So let's think of this kind of reduced echelon form. Okay, so suppose we obtain this kind of pattern as our reduced echelon form. So in this case, we know that these two are basic variable, and these are free variables. But here, we can see that the pivots are existing in the rightmost column or the last column. Okay, but the last column is not corresponding to one of our variable, but it's actually corresponding to the constant values that we find on the right hand side of our equations, right? So in this case, let's look at the equation form of this last row that has the pivots in the last entry or the last column. So in this case, it will be 0 times x1, 0 times x2, and so on. 0 times x4 is equal to some non-zero value, right? So this equation is impossible to satisfy because the left-hand side, which has all the coefficients as 0, so for any any set of x1, x2, and x3 and x4, it will always remain as 0, but the right-hand side is some non-zero, which is impossible to satisfy. Okay, so once we obtain this kind of pattern in our reduced echelon form, then this is when our linear system has no solution. Okay. So in this case, really the simple case corresponding to this case is as follows: 1, 2, 3, and 2, 4, 7. Okay. So in this case, we have 2 variables and 2 unknowns, and then it's a 0, 0, and 1, right? And so pivots are already found over here. So the second equation is 0 times x1, 0 times x2 is equal to 1, which is non-zero, which is impossible to satisfy. Okay, so in this case, we cannot find any solution. So no solutions exist in this case. So back to this theorem. While doing this Gaussian elimination, okay, I mean, so even though I mentioned it as a reduced echelon form, but another kind of another pattern or another property between the echelon form and the reduced echelon form. I mean, I already mentioned that during the first phase or the fourth phase of Gaussian elimination, the resulting matrix is a echelon form, or that satisfies the echelon form. And then after doing the backward phase and then completing that Gaussian elimination process, the resulting matrix will satisfy reduced echelon form, right? And so in the middle of this process, we obtained echelon form and the reduced echelon form. And then now let's think of the pivot position, okay? Pivot position. So during the second phase of this backward elimination, it doesn't change the pivot positions, or it doesn't add or remove the existing pivots that were found in our echelon form. Okay, so suppose this guy is some echelon form that we obtained, okay, as an output of the first phase Gaussian elimination. Okay, and then now the second phase will not change those pivots, but we only remove this guy as 0, right? And so can we make this guy as 0? No, because it will be 0. So for whatever values that we multiply this with, for -4 and 5 and 6, and then adding it to the upper rows, right? So it cannot affect those pivots on the left side, right? So we will only make the upper entries of the existing pivots, okay? And in this process of the second phase, the pivots, the pivot positions or the number of pivots will not change at all, okay? So if you want to see the patterns of, or where the pivots are found, and then it's just enough to perform the first phase of a Gaussian elimination, okay? Okay, So once we perform this first phase of a Gaussian elimination, and then you suppose you found the pivots in the last column, just like this case, where we have still non-zero in the upper part. Okay, so in this case, that's when you can say that this linear system has no solution error. Okay, and in this case, yeah, let me ask this: does this linear system has a free variable or not? Are there free variables in this case? I mean, by the definition of the free variable, what was the definition of the free variable? I mean, the columns that doesn't have any pivots. Okay, those corresponding variables are called free variable. So in this case, even though this linear system has no solution, but this linear system has free variable by its definition. Okay, so we have these two free variables, right? But in this particular case, should we represent this solution as like, okay, let me just fill up these numbers. Yeah, if it is a reduced echelon form, it is 1 and maybe 2, and yeah, it should be 0 and 3 and 0, right? And then it can be 2, for example. So this is still a valid reduced echelon form, right? And so in this case, this guy can still be represented as a parametric description of our solution. x1 is equal to -2 times x2 and -3 times x4, right? But we have 0 on the right hand side, right? So we can write these equations by following the specific rule that we studied, but there is no point. I mean, you don't need to do so, okay? Because this guy is, yeah, I mean, there is no solution exists in this case, right? So there's no point of writing the parametric vector, I mean, parametric description of our solution, because no solution exists simply. So yeah, in summary, which condition or which situation do you need to first check? Okay, so once you obtain this echelon form, you have to first check whether you found this kind of row that has the pivots on the right, I mean the last entry, because that will correspond to 0 times, and 0 is equal to non-zero, right? So in this case, yeah, we have no solution at all, right? So that's just okay to stop at that point, okay? But once you found there is no such columns, which means the last column doesn't have a pivot, okay? Last column doesn't have a pivot. So in this case, you go on, I mean, yeah, you can go on with the second phase of a Gaussian elimination, and then if you have a free variable, then you obtain the parametric vector form as your final answer. And yeah, and, in that case, yeah, and also, yeah, in that case, if you find the free variable, and then that's when you have an infinitely many solution, right? But if you don't have any free variable, okay, if you don't have any free variable, and that's when you have a unique solution, because there is no free parameter or free variable to freely assign as an any value. Okay. So this is how we determine the number of solutions of a given linear system. So again, there are 3 possible cases: no solution at all, and if the solution is existing, and then a unique or infinitely many solution. Okay. And then the first thing to check is whether we have this kind of pattern, or the last column is having the pivots. Okay, in that case, we can conclude that we have no solution at all, right? And then if there is no such column, I mean no such cases where we don't have any pivots in the last column, and then we move on to obtain reduced echelon form. And then if we have if we have a free variable, and then that's that's when we have an infinitely many solution. And if we have no free variable, which means all the variables are basic variable, or in other words, every columns in the except for the last column corresponding to the constant, the last, I mean the left, all of the left columns have a pivots. In that case, all of them are basic variables, and thus in that case the solution is unique. Okay. Okay, and then using this properties or patterns, let me ask some simple question. So suppose you have this size of an augmented matrix of 3 by 5. Okay, so in this case, let me ask you guys whether this it is possible that this linear system has a unique solution. So again, given this shape of a matrix of 3 by 5 as our augmented matrix, and then is it possible that we have unique solution? It is not. Yeah, so the reason is because so in order to have at least one solution, so the last column shouldn't have a pivot, right? Okay, then let's suppose we satisfied that condition. We avoided that unfortunate situation. And then now let's assign those pivots to our variables. So in this case, except for the last column, we have 4 columns or 4 variables, right? And then how many pivots can we maximally have in this case? So we have 3 rows, only 3 rows, right? So we only have 3 pivots at most, right? So some kind of an X mark is distributed, have to be distributed among 4 of these rows, right? But we only have 3 X marks, so it can be like this, or it can be like this, or it can be like over here, and over here, right? So 4 variables, and then 3 pivots, and thus it means it is always the case that we always have at least one free variable. In this case, there is no such case. I mean, it is impossible that we have an infinitely many solution. It is impossible that we have a unique solution, right? And also, let's also think of the number of variables and equations in this case. How many equations? We have 3, right? And then how many variables? We have 4 variables. So 3 equations and the 4 variables, and we intuitively know that using this less number of equations than the number of variables, so we cannot obtain the unique solution, right? So that can be also explained or understood by having this kind of pivot positions and their patterns in our matrix. Okay. And then in this case, is it possible? Is it possible to have 2 or less, even less number of pivots? So instead of 3 pivots, is it possible that we have only 2 pivots? It is possible because, for example, in this case, right? So we have a pivot over here. So even though we have 3 rows, so the last row is no longer exists in this particular case, and so the pivots are only existing in the first and the second row. So in this case, even though we have 3 rows, it is possible that we have a 2 or even less number of pivots, right? And then we can also think of many different cases by only considering this matrix shape. Okay, so in this case, we understood that the unique solution is not possible or impossible in this particular case. But let's also think of like this case. So we have 5 rows and 3 columns in our augmented matrix. Okay, so let me ask the number of solutions, possible number of solutions in this case by considering the pivot positions and their patterns. Okay, so in this case, I mean, is it possible that we have no solution at all in this case? Yes. So let's suppose we have a pivot over here. So in this case, we have the pivot on the last column. So no solution, right? And also in this particular case, what can we say about the last two rows? The last two rows should be completely zero, right? I mean, if this is our echelon form as an output of the the Gaussian elimination. Okay. Okay. And then what about the other pivot cases? Is it also possible that we only have just two pivots in this manner? So our staircase shape is just like this. Would it be possible? Yeah, it is possible. So the simple case is like 1, 2, 3, and 2, 4, 2, 5, and maybe 1. And then the remaining three rows are trivially the multiple of the first equation of 2, 4, 6, and 3, 6, 9, and 4, something like that. Okay. So while using this as an eraser, and then erasing each of these, and then these will be completely gone. Okay. So this one is one particular example where we have completely zeros for the last three rows, right? So still the pivot pattern, I mean this kind of pivot pattern is possible. So in this case, is the solution, does the solution exist? Solution exists because the last column doesn't have any pivot, right? And then the next question is, okay, so we found that the solution exists, and then is the solution unique or infinitely many? So do we have a free variable or not? Okay, so that is the way of answering this question. So we have two variables and two columns are all containing the pivots, and they are all basic variables. So in this case, the solution is unique. Okay, and then suppose we have a pivot only on this part. Okay, and that's it. So in this case, we have a free variable on the second column, right? And so we can have infinitely many solutions. Okay, and then in this particular case, all the three cases are possible depending on the possible pivot position patterns, right? But in general, we know that like we have a 5 equations and only 2 variables, right? Again, the 5 equations and 2 variables. In this case, yeah, it is likely that we have no solution at all because simply because we have more number of equations than the number of variables, right? So that is corresponding to like having some pivots like in this part, okay, on the last column, okay. But luckily, if we have no pivots on the last column, then we can still have the solution. Any questions so far? Okay, then that's it for today, and and so the first homework will be posted probably today or tomorrow. Okay, and usually the given time until your submission of your homework will I'll give probably 1 week for each homework. So once the homework is posted, and then you will have 1 week to submit your homework.
그러면 로우 익스체인지나 로우 스케일링에 따라서 프리 베리어블이 바뀔 수 있는 거예요? 한그 매트릭스 안에서도
네.
프리 베리어블은 계속 바뀔 수 있는 거예요? X가 됐다가 X가 됐다가
그게 그러니까 우리가 정확하게 그 가우시안 엘리미네이션에서 아까 이야기한 그런 롤을 따르면 그러면 이제 그 로우 익스체인지나 이걸 하더라도 익스체인지 한 다음에 그 이제 위에 있는 거에 가장 첫 번째 베리어블로 이 밑에 걸 지우잖아요. 그러니까 이 로우를 바꾼다고 한들 실제로 이 컬럼에서 어디에 피벗이 위치할 것이냐를 얘가 바꿔주진 않아요. 네, 그래서 이제 그 누가 프리인지 그거 저기 베이직 베리어블인지는 이게 있었다고 해도 안 바뀌어요. 네.
그 아까 영영에 대해서
네.
여길 때그
네.
x1하고 x2를 x3로 표현해가지고
네. 네.
그 descriptive parameter 해가지고 넣는 거에 따라 답이 몇 개 나왔잖아요. 그때 마지막에 0000이 아니고
네.
000 막 3 이렇게 나와도
그러면 이제 답이 없다라고 그냥 결론을 내리면 되는 거죠.
이때랑 이때는 다른 거예요?
네, 이거를 그러니까 여기 3이 있을 때 위에 거로 이렇게 나타낼 수는 있지만 이 위에 거 식으로는 뭐 예를 들면 이렇게 파라메트릭 폼으로 나타낼 수 있겠지만 이거는 결국 마지막 이퀘이션을 우리가 만족할 수 있는 방법이 없다는 뜻이거든요.
x1, x2, x3 뭐가 들어가도 3을 만족시켜야
네,
되니까.
네.
그래서 그 아까 유닉 막 티어엠이
네,
이 마지막 게
네.
피벗이 되면은 답이 없다 그런 게
맞아요.
거예요.
네, 맞아요.
그러니까 0000일 땐 답이 있는데 3일 땐 답이
그렇죠.
없다
그렇죠.
이렇게
네.
나와요.
그러니까 결론적으로는 맨 마지막 컬럼에 피벗이 존재하면 그건 답이 없는 케이스고 왜냐하면 0000 이퀄
하는 x,
난지로니까
x2, x3가 답이 전혀 있을 수가 없어요.
없으니까요. 우리는 하여튼 모든 이퀘이션을 다 만족하는 솔루션을 찾아야 되는데 그 중에 하나가 지금 만족이 안 된다는 걸 우리는 알았잖아요. 그러니까 이 답이
디스크립션이
필요가 없-
무조건 다 0000이었다는
그렇죠. 있다면 0000. 네.
백골드 할 때 피봇이 원래 이렇게 되는데
네, 네.
이거 기준으로 보여주신 게
그거는 이게 그렇게 하지 않는다는 거죠. 그러니까 이거를 했을 때는 어떤 그러니까 다른 형태의 파라메트릭 폼을 얻을 수가 있다라는 것을 보여줬지만, 그래서 이것도 사실 이 이퀘이션의 이 연립방정식의 솔루션인 거는 맞아요. 근데 우리는 이렇게 안 나타낸다는 거죠. 이렇게 따지면 사실 그 솔루션이 다 누가 푸느냐에 따라서 그게 다 달라질 수 있거든요. 그래서 이제 그게 조금 막 중구난방이 될 수 있으니까 우리는 항상 이 룰을 따랐을 때는 언제나 이제 항상 동일한 이제 파라메트릭 폼을 얻게 돼요, 우리는.
그리고 이렇게 요 예시에서
네.
마지막에 피봇을 만들잖아요.
네.
저는 피봇이 밑에 거를 지우기 위해서 설정한다고 했는데
네네.
얘는 이미 지울 게 없는데 왜 피봇을 설정하는
왜 피벗을 설정하냐고요? 그게 이제 마지막에 지울 게 없어도 우리는 그 피벗을 고려를 하기는 해야 돼요. 왜 고려를 해야 되냐면 제가 예를 들면 아까 얘기했던 것처럼 뭔가 마지막 컬럼에 위치하는 피벗이면은 그러니까 그 피벗을 따져야 마지막 컬럼에 이제 그 피벗이 위치하니까 솔루션이 없다라고 결론을 내릴 수 있잖아요.
네.
그래서 이제 마지막 거에서 이제 지울 게 설사 없어도 우리는 그것도 우리의 이제 정당한 하나의 피벗으로서 고려를 하기는 하는 거죠. 그러니까 그걸로 이제 지울 건 없으니까 그걸로 뭐 말 그대로 지우는 작업을 전혀 하지 않아요. 그렇지만
근데 만약
걔도
100골드 할 때는
네네.
이 피봇이 중요하.
그렇죠. 그거 중요하죠. 왜냐면 그 위에 거를 지워야 되니까. 네.
합니다.
중간에
네.
피봇이 아예 없는 경우도 있다고 하셨던 것 같은데 그럼 그냥
피벗이 아예 없는 경우요.
네,
피벗이 아예 없는 경우는
그냥 다 제로.
그렇죠. 다 제로인 거죠. 그거는 이퀘이션이 아예 그냥 다 0으로만 구성되었던 이퀘이션이라는 뜻이거든요.
네.
그래서 지금 수업이 있어서 일단 나가서 내가 질문을 받을게요.
숙제는 블랙보드에 올라오는.
네네, 블랙보드에 올라와요. 네.
숙제를 내는 방식.
내는 방식은 아마 이메일로 내가 공지를 해줄 건데,
네.
손으로 풀든 아마 이렇게 뭐 이렇게 컴퓨터로 하든 뭐 그렇게 해서
이거
아마
찍어서 올리는.
네네 맞아요. 네 그렇게 하면 돼요.
그다음에
네.
성형계 해가 없어도 자율변수, 기본 변수 좀 인지한다고
네.
하셨던 것 같아요.
뭐가 없어도요?
그래도 이행렬인 경우
네.
마지막에 이 부분에 1이 있어서 성형계 해가 없잖아요.
네.
그럼 이 경우에서 이쪽이랑 이쪽은 기본 변수, 이쪽이랑 이쪽은 자율변수다.
맞아요. 네.
그렇게 되는
그러니까 맞아요. 조금 뭐 헷갈리게 얘기했을 수 있는데 걔네들이 자유변수인 거는 맞아요. 자유변수인 거는 맞지만 그냥 걔네들은 자유변수일 뿐이고 기본적으로는 마지막 컬럼에 이제 피벗이 있었기 때문에 마지막 컬럼에서 이제 피벗이 이제 존재했기 때문에 해가 없는 거죠. 해가 없기 때문에 뭔가 우리가 그 파라메트릭 폼으로서 이제 자유변수를 오른쪽으로 다 옮겨서 이제 식을 나타낼 필요가 없는 거예요. 왜냐하면 이제 솔루션 자체가 이제 마지막 그 이제 어떤 이퀘이션 하나를 이제 만족을 우리가 못 하기 때문에 그렇게 쓸 필요가 없는 거죠. 네.